So the method of steepest descent is also known as the method of gradient descent, and it's a popular optimization algorithm which is used to find the minimum of a function. So the method involves iteratively adjusting the parameter of a function in the direction where the descent is steepest until a minimum value is reached. So some key points to note about this method. One is the direction of the steepest descent. So at any given point of the function, the steepest descent direction is the direction in which the function decreases the fastest. So this direction is given by the negative of the gradient of a function evaluated at that point. Now, if we consider a function of n variables, then the gradient is a vector of partial derivative. So that if we consider, for example, a function with two variables, x and y, then the gradient, which we use the symbol nabla, evaluated at some point, xy, will be a vector comprising of the partial derivative of f with respect to x and the partial derivative of f with respect to y. So that in this case, the vector has two components, the x component being the partial derivative of f with respect to x, and the y component is the partial derivative of y with respect to x. Number two is the algorithm. Now, the method of steepest descent works by iteratively adjusting the parameters of the function in the direction where the descent is steepest. So at each iteration, the current value of the parameter is updated by subtracting a small multiple of the negative gradient evaluated at that particular point. So this multiple, we call it the running rate or even the step size. And it is this value that determines how quickly the algorithm will converge to the minimum. Number three is about the convergence. It is important to note that this method may converge to a minimum value of the function, but does not guarantee that the global minimum will be achieved. So the algorithm is usually used to find the local minimum of a function. So that in this case, when using the algorithm, you may not be expecting to find the global minimum, as the algorithm may get stuck at some local minimum or even a saddle point, and which will be difficult to escape. Now, the convergence rate of the algorithm is based on the curvature of the function, the step size, and also the point where you start, that is your initial approximation. If the step size is taken to be a large value, then the algorithm may never converge. It may overshoot the minimum and oscillate around it. Now, some of the applications of the method include in the use of the method in training the neural networks or linear regression models, logistic regression, and other models that may involve minimizing the loss function. So generally, steepest descent is usually used in machine learning and optimization. So in general, we are saying that the method of steepest descent is based on the observation that if a real-valued function f is defined and differentiable on the neighborhood of some point x naught, then f will decrease the fastest if one goes in the direction of the negative gradient of f from the point x naught. So it follows, therefore, that if we define x1 as x naught minus t times the gradient of f evaluated at x naught for some value of t greater than 0, then f of x naught will be greater than f of x1. So with this observation in mind, One starts with the initial guess, which is x naught for the local minimum, and then consider a sequence of vectors x1, x2, x3, such that xk plus 1 is equals to xk minus t times the gradient of f evaluated at xk. So for k, taking an integer value from 0 to 1, 2, 3, 4. Now, the value of t is determined such that the function g, which is defined as f of xk plus 1, is a minimum. Now, we take an example. We consider a function of one variable defined by x squared plus 2x minus 1. And the problem will be to find the minimum value of this function using the method of steepest descent. And we are going to start with the initial approximation x naught as 0.8. So the first thing is to compute the gradient of f. So when we write the gradient of f here, because f is a function of one variable, then this will be the same as the derivative of f with respect to x, which we can denote by f prime of x, and is given by 2x plus 2. That is the gradient of f. Now, next is the initial approximation, which we have said we are going to use a value of 0.8. Then we construct the iterative procedure. Xk plus 1 is equals to xk minus t times f prime of xk. But f prime of x is 2x plus 2. So that this method, we can now write xk plus 1 is equals to xk minus t times 2xk plus 2. We can write our method in this form so that now k starts from 0, 1, 2, 3, and so on. This is the iterative procedure. Now, the value of t is determined such that g of t, which is equals to f of xk plus 1, is a minimum. Now, when we want to minimize a function, we differentiate this function with respect to the variable, which in this case, our variable is t, equate the derivative to 0, and solve the resulting equation. So we can write g of t is equals to f of u, which is equals to u squared plus 2u minus 1. Remember how our function f of x was defined. It was x squared plus 2x minus 1. That was the function. So when we replace with u, x with u, we get u squared plus 2u minus 1. Now here, u is equals to xk plus 1, which we have as xk minus 2xk plus 2 multiplied by t. So that if we want to differentiate g with respect to t, g prime of t, we can write it as the derivative with respect to t of f of u. And this we can achieve this derivative by using the chain rule. We differentiate f with respect to u first, and we multiply by du dt. And you can see that the derivative of f with respect to, because f of u is this function here, if we differentiate that with respect to u, we get 2u plus 2. Then the derivative of u with respect to t, u is this one. So when we differentiate, we get minus 2xk plus 2. So this is the function g prime. This is the derivative of g. So if we want to minimize g, we equate the derivative to 0 and solve the resulting equation. So the derivative that we must equate to 0 is 2u plus 2 multiplying minus 2xk minus 2. We equate this to 0. We can divide this side by 2xk minus 2 minus that. We divide here by the same, minus 2xk minus 2. And this will give us 2u plus 2 is equals to 0. But we know that u is equals to xk minus t into 2xk plus 2. So that when we write 2u plus 2, now this one becomes xk minus t into 2xk plus 2, then plus 2, which is xk plus 2. Sorry, there is a 2 here that multiplies the whole of that. So we get 2xk plus 2 minus 2t into 2xk plus 2, which now we equate to 0. This is what we are going to equate to 0 as per this equation. So we write 2xk plus 2 minus 2t into 2xk plus 2 is equals to 0, meaning that 2xk plus 2 is equals to 2t into 2xk plus 2. And from here, we can find t is equals to 2xk plus 2 divided by 2 times 2xk plus 2, which is equals to 1 over 2, or 0.5. So this is the value of t that minimizes the function g. This is the value of t that minimizes the function g. So once we determine the value of t, in this case t is a half, is a constant, then we can go back to our iterative procedure. Our iterative procedure was xk plus 1 is equals to xk minus t df of xk, which we had obtained as xk minus t into 2xk plus 2. Then k starts from 0 to 1 to 2 and so on. So that when k is 0, this will be 0 and this will be 1. So we get x1 is equals to x naught minus t times 2x naught plus 2. But x naught is 0.8. That was the initial point. X naught was 0.8. So we're going to substitute here. We get 0.8 minus 0.5, which is the value of t, times 2 times 0.8 plus 2. This will be 2 times 0.8 plus 2 is 3.6. We multiply that by 0.5 and then subtract from 0.8, we get minus 1. We now repeat the process for k is equals to 1, so that we put 1 here, then we get xk. This is xk plus 1. So when we put k as 1, this will be x2, this will be x1, x1 here. So when we do that, we see that now we have x1 minus t, 2x1 plus 2, but x1 is minus 1. So we substitute and we get the result again, x2 is minus 1. So basically here, the method has converged to minus 1. We don't need to perform so many iterations. This is the case where we have t here was a constant, half, But in the case where the function f has more than one variable, t may vary from one iteration to the next. T may vary from one iteration to the next. Let's consider the case where we have a function of two variables. We have a function of two variables here, 4x squared minus 4xy plus 2y squared. So when we write the gradient of f, this will be the partial derivative of f with respect to x and the partial derivative of f with respect to y. We are going to have two items, two elements there. So this is a vector with two elements. Now, our function f here, our function f is equals to 4x squared minus 4xy plus 2y squared. So when we differentiate f with respect to x, we get 8x minus 4y. And when we differentiate f with respect to y partially, we get minus 4x plus 4y. So that our gradient, the gradient of f, when we write the gradient of f, then this will have the x component as 8x minus 4y and the y component as minus 4x plus 4y. This will be our vector, our gradient vector. Then we can evaluate this at different points. So our initial point here, the initial approximation is x naught is 2, y naught is 3. So that if we want to evaluate this at that point, if we now write the gradient of f evaluated at 2, 3, then we shall write this is 8 times 2 minus 4 times 3. That is the x component. The y component will be minus 4x minus 4x. X is 2. So minus 4 times 2 plus 4 times 3, which is y. And this will be 16 minus 12, comma, minus 8 plus 12. And we say that this will be 4, comma, 4. So that will be the value of the gradient at the point x naught is equals to 2, y naught is equals to 3. So in this case, our method, now we have the same method as before. Remember our method was xk plus 1 is equals to xk minus t times the gradient of f of xk. But now, our point here is not just one value, xk. We have xy. So we replace x here with x comma y, the vector, so that we get xk plus 1 comma yk plus 1, which will be equals to xk comma yk minus t times the gradient of f evaluated at xk, yk. If we put k is 0, this becomes 0, 0 here. If we put k is 0, then we shall get x1 comma y1, which will be equals to x naught comma y naught minus t times the gradient evaluated at x naught comma y naught. And we know that we have obtained this quantity here. This quantity, we have worked it out here and we have obtained 4, 4. So which means that we can substitute that value. So we have now to minimize the function g of t, which is now f of xk plus 1, comma, yk plus 1. So in this case, we have f of x1, comma, y1, which we have x1, comma, y1, where x1 is given by t, or rather 2. x1 is given by x0 minus t times the gradient of f evaluated at x. Sorry, we cannot write that. When we write x1, let me write it on this, on a fresh page here. When we write x1, comma, y1, this will be x0, comma, y0 minus t times the gradient evaluated at x0, comma, y0, so that this will be 2, comma, 3, which is the initial point, minus t multiplying 4, comma, 4, because we had already obtained this quantity here. So that we get 2 minus 4t, comma, 3 minus 4t. So in this case, x1 is 2 minus 4t and y1 is 3 minus 4t. So those are the values. x1 is 2 minus 4t, y1 is 3 minus 4t. Then we now differentiate g. So we write, in this case, g of t is equals to f of 2 minus 4t, which is the x component, and 3 minus 4t. So when we write g prime of t, this is the derivative with respect to t of f, which we write as the partial derivative of f. Remember, f was defined in terms of x times dx by dt plus the partial derivative of f with respect to y. Remember, f was also a function of y, dy dt. That is, we use the total derivative. The total derivative of f with respect to t is the partial derivative of f with respect to x times dx dt, and the partial derivative of f with respect to y times dy dt. Now, we had seen that the partial derivative of f with respect to x is 8x minus 4y. And the partial derivative of f with respect to y was minus 4x plus 4y. So those ones we can substitute. Then we have dy by dt. But we have also seen that in our case here, x is equals to 2 minus 4t and y is equals to 3 minus 4t, meaning that we can differentiate. We have seen that x is equals to 2 minus 4t and y is equals to 3 minus 4t, meaning that the derivative of x with respect to t is negative 4, and the derivative of y with respect to t is also minus 4. So we are going to substitute these two in this expression and then simplify. We substitute these two, minus 4 here and minus 4 here, then simplify. So this is what we do. This is the g prime. Then we find the partial derivative of f with respect to x. We had already determined that. Partial derivative of x with f with respect to y. X is this, y is that. So dx by dt is 4 minus 4. dy dt is minus 4. We substitute these quantities here and simplify. So g prime becomes negative 16x. But x is known to be 2 minus 40. It means that we substitute here. We get 64 minus that 2. 6040 minus that 2. Now, for g to be a minimum, then g prime must be 0. So we are going to equate this expression, 6040 minus that 2, to 0. And then we get t is equals to that 2 over 64, which in this case is a half. So once we get the value of t, then we can get the next value of x and y. The values after the first iteration, x1, y1, which we write x0, y0 minus t times this. We have now x0, y0 is 2, 3, and this gradient we had determined as 4, 4, and t we have obtained the value of a half. So x becomes x, which is equals to 2 minus 40, becomes 2 minus 4 times a half, which is 2 minus 2, and this is 0. Y, which we had written as 3 minus 40, becomes 3 minus 4 times a half, which is equals to 3 minus 2, a value of 1. So x1 is 0, y1 is 1. So now we repeat this procedure to find x2, y2. So x2, y2 is now expressed in terms of x1, y1. So x1, y1 minus t times the gradient of f evaluated at x1, y1. Remember, the gradient of f evaluated at a point x, y, we had already worked out this was 8x minus 4y, minus 4x plus 4y. So when x is 0, when we write df of 0, 1, then we shall get 8 times 0 minus 4 times 1, which will give us minus 4. Then the next point will be minus 4 times 0 plus 4 times 1, which is 4. So that one will be determined as 4 minus 4, 0. And now we determine g of t. G of t, which is equals to the gradient of f evaluated at the point x2, y2. As before, we have we can determine x2, y2. You can determine x2, y2. Let me do it on another page here. We can write that x2, y2 is equals to x1, y1 minus t times the gradient of f evaluated at x1, y1. We know that x1 is 0, y1 is 1, then minus t. The gradient we have obtained value of minus 4, 4. So that this becomes 0 minus t into minus 4, 1 minus t times 4. So that this is positive 40, 1 minus 4t. So here, x2, we can write x2 is equals to 40 and y2 is equals to 1 minus 4t. And so we can differentiate. The derivative of x2 with respect to t will be 4, but the derivative of y2 with respect to t will be minus 4. So these are the values. X component is 40, Y component is 1 minus 40. And then we can find G prime again. Here, X is 40, Y is 1 minus 40. So when we differentiate, the partial derivatives are the same as before, 8x minus 4y and minus 4x plus 4y. So the only thing that is changing is the derivative of x with respect to t and the derivative of y with respect to t, which we now have 4 and minus 4. So when we simplify this, we get 48x minus 32y. But x is 40 and y is 1 minus 40. So we can simplify this to get 320t minus 32. But for g to be a minimum, then the derivative must be 0. So that in this case, again, we now equate 320t minus 32 to 0. And this will give us t is 32 over 320, which is 1 over 10 or 0.1. Now with this value, we can determine the value of x2, which we had written as 40, and y2, which we had obtained as 1 minus 4t. So 40 will be 4 times 1 over 10, which is 2 over 5, or 0.4. And this will be 1 minus 4 times 1 over 10, which is 6 over 10, or 3 over 5, or a value of 0.6. So these are the values of x2 and y2. So we can repeat this procedure many times until we get the convergence of the solution. So we can write x3, y3 in terms of now x2, y2, and work out the same procedure to get the value after the third iteration. We can do the fourth iteration and so on. So this procedure can be repeated many times until we get the convergence of this method. So basically, this is how the method of steepest descent works. The method can be applied when we have a function with many variables, or even when the function has only one variable. But for a function of one variable, it is easier to sometimes just differentiate and equate the derivative to 0 and solve the resulting equation because it is just one. But when we have more than one variable, then as the number of variables increases, then we may need to apply this method and maybe write an algorithm, which we can even use a computer program to solve. Computer programs can carry out these operations very fast and get the solutions. Even with 100 iterations, the solution can be obtained very fast. So basically, that's in a nutshell is the method of steepest descent.